All right. Howdy. Thank you all for being here. I am Mr. Simonian. I am going to be your instructor for reactor analysis this summer. Today is the first day of class. We're just going to go over introductory kind of stuff. I'm going to talk about the syllabus and then going to try to get through that as fast as possible so that we can get into the introductory material for today, which will mostly be, well, it'll pretty much entirely be 301 review, just to make sure we're kind of all on the same page with terminology and basic definitions before we get into new stuff. So thank you all for being here, and I'm looking forward to a good class, and I hope you are too. Um, about me, again, Mr. Simonian, I technically professor is like a title, which I'm not a professor yet. If you call me Professor Simonian, I won't correct you, because that is what I eventually want to be, but you can just call me Mr. Simonian for now. I grew up in Austin. I went to McCallum High School. I was not a good high school student. I was doing other things when I was in high school besides caring about school. I ended up at ACC, Austin Community College, once I left high school. When you start at community college, you take the placement test to figure out where you're at in different stuff. I failed the math TSI, so they started me out in elementary algebra. And I knew that I wanted to do, at that point, I wanted to do chemistry. And so I knew I had to take math classes. And so I worked my way through all of the different math that they had at ACC. Eventually, sometime while I was there, I realized I actually wanted to do engineering. So when I transferred here for nuclear engineering. I got my bachelor's here, and then I worked for a little bit. I graduated in 2018, which wasn't the best time to graduate as a nuclear engineer. So I spent some time as a tutor while I was in college. I spent some more time as a tutor once I graduated, and then I realized I'm already tutoring. I'm not finding a full-time engineering job. Let me do something that's kind of close to what I want to do, which was teach. So I did an alternative certification program to become a teacher. I taught at Manor ISD for 3 years, which is just a small town outside of Austin, and I taught physics. Um, I was a teacher from 2019 to 2022, so I taught all through COVID. It was kind of rough. I realized how much I liked teaching, but that I didn't really want to keep teaching at the high school level. And so that was when I decided to come back to grad school to get my PhD. So I've been a graduate research assistant for my entire time here. I work under Dr. Mark Kimber in the thermal hydraulics V&V lab. Um, I did a summer internship at Oak Ridge, and I've done teaching. I taught this class last summer, and then I'm teaching it again this summer. On the research side, I do a lot of CFD. CFD is cool because the Navier-Stokes equations are too hard to solve by hand, but you can numerically solve them using computers, and that's how you can do flow modeling of a reactor core or some some complicated geometry. Um, my dissertation is very heavy into systems modeling using a code called Relap 53D. Um, we are working on the molten salt project that's happening over in Abilene, and our group is doing all of the modeling of that system. So we're modeling the core, the entire primary loop, the entire secondary loop, and the tertiary air loop. You can model that in this program, and then once you've built out the reactor, you can do different kinds of things to it. Like you can do a reactivity insertion and see what happens to your temperature and your power and things like that. So yeah, that's what I'm doing right now for my dissertation. It involves it's in the realm of advanced reactor design, analysis, optimization. It's also in the world of nuclear thermal hydraulics because um, what happens in the reactor core influences what happens in the rest of your plant. What happens in terms of your heat transfer and your fluid flow will impact your reactivity and your nuclear physics, and those kind of feed into each other. So that's the world of thermal hydraulics. And then verification and validation is all about when you are using computer codes, like if you're running CFD or if you're running relap or any kind of computer program, you want to be able to make sure that the computer program is doing what you think it should be doing. And so verification and validation is the process by which you can check your code, check for errors in your code, check for the order of accuracy of the outputs that your code is generating. And then the validation part is where you compare your results against like experiments or other real data so that you can have confidence that what you're simulating matches the physics that you would expect. And then I'm also very much interested in STEM education. As a teacher, I learned a lot about, I was teaching physics, so there's a big body of physics education research out there. So I've learned a lot about learning styles, about different approaches to learning, active learning, and hopefully I'll be able to integrate those things well into this course. So the next thing that I wanted to go through was the syllabus up here. There's a copy of that. If you didn't grab one, please do. This is a 3 credit hour course, Monday, Wednesday, 1:20 to 3 p.m. Um, We'll talk about what 304 is about in a bit. I wanted to mostly just cover like that kind of odds and ends of the syllabus. We'll be meeting here for our lecture. If you look near the bottom where it says instructor details, my email is the best way to reach me outside of class if you have questions or need help with something. I'll be planning to do office hours after class for an hour in my room in the AIEN building. That office is M104, so M is the main building, not the annex. Um, if you walk in that main building where there's all the construction and you see the big fancy staircase, if you go to the left, like down that hall where Mariano's like detector room is, 104 is on the right, just past the stairs. So on the first floor, that's where you can find me. If you want like individual one-on-one help for questions that can't be answered over email, that would be the place to go. And then if those times don't work for you, that's okay. Just reach out to me over email if you want to schedule like alternative office hours. I will work with your schedule as best I can. And in terms of like emails and stuff, I'll always try my best to respond within 1 business day. So like if you message me on Monday, I'll try to get back to you by Tuesday. But if you message me like on Friday, then I might not get back to you on until Monday. Um, the second page just talks about prerequisites. I assume we've all done reactor theory and we've done linear algebra. Those are the prerequisites. Um, Learning objectives, we're going to kind of go through that as we go through the class, but that gives you an idea about what to expect. Um, in terms of resources, I have a class Google Drive that I'm going to be using to share a lot of materials. You should have already gotten an invite to that Google Drive. Like if you're on your Google Drive, if you go to shared drives, you should see one that says new in 304 summer 2026. This is where I've posted the syllabus. This is where I will post our practice problem sets. Um, all of my lectures are going to be here. So, like, if you go into blank presentations, that would have been where you could have found the slides for today. I will always have this updated before class, like the day before, so that if you are trying to like print the slides out, I won't print the slides out every time because I don't like wasting paper. So that'll be there for you in advance so that you can print them out or you can access them however you feel comfortable. If you're like doing notes on the tablet, then it would probably be better to just like download the PDF and do it that way. But that's where you can find those. After class, I'll fill in. I'm gonna be writing on my slides and I'll upload those into here once I'm done. I will also be recording the lessons, and then I'll post those online too, so that if you like miss a class, it will be hopefully relatively easy to catch up because you'll have the completed notes, you'll have the recording, and that should be everything you would need to catch up on what you might have missed. Um, Whenever we have quizzes, I'll post the rubrics and the solutions here. And then there's also a resources tab. This has a couple useful documents. The main kind of textbook that we have for our class are the reactor analysis notes from Dr. Svetkov. But I've also posted a couple other pieces of resources that are useful. The Duderstadt book is another good reactor analysis book. The Dr. Adams reactor theory notes, or if you had Dr. Fiorina for 301, I believe they're the same notes. That's a good place to get like kind of background information. Um, I put together this study sheet, which has some of like the introductory equations that we will need or that we will be using. The first two pages I think are relevant to 301 and 304. Once you get to this third page, it's kind of getting into more graduate level stuff. So definitely like I would probably ignore the third page. But if you this kind of has a lot of essentials all in one place. So that's why I call it the essentials study sheet. Um, and then this is a document from the IAEA that has a lot of material properties that might be useful. And then this was a suggested reading out of the LaMarche book. Um, but I think I took out that problem from the problem set, so you probably won't need that. But it has some interesting introductory info about nuclei, magic numbers of nuclei. So yeah, basically, this is our shared Google Drive. It's a place where you want to be able to get access. You should all have access through our group. But if for some reason you don't see this Google Drive, if you just shoot me an email or let me know after class, and I can get you added to that. Um, so that should cover lecture presentations. The lecture recordings, there's a YouTube channel that I will be putting those on. I already have all of the recordings from last year there, and then I'll upload as we go the recordings from this year too. At the end of the third page, you see the grading policy. Um, in this course, that's showing you where our grades are going to be coming from. So we're going to do quizzes. There's going to be a reactor design problem. There's going to be two midterms, and then there's going to be a final exam. And then if you look on the right, it shows the element score for those things. There's a range of values for those deliverables, which means that whenever I am doing your grades at the end, I will pick those scores so that they maximize your overall grade. So, like, maybe we don't do so well on midterm one, but we do really good on midterm two. So, midterm one would be at like a lower range of the weights, and then midterm two would be like at a higher range of the weights. Instead of curving, I will just that's kind of the way that I end up curving the class. And it'll have a normal a, B, C, D grading scale as shown on the bottom of that page. On to page 4. I'm going to do quizzes kind of pretty much every day. I would probably expect a short quiz, 5 to 10 minutes over what we had covered in like the previous lesson. Those will be closed book, closed notes, no calculator, and they will be very heavily based on what we talk about in class, as well as some of the suggested practice problems. Um, so yeah, we're gonna have two midterms. Those will also be in class, closed book, closed notes, no calculator. I will provide a review for that. I am still kind of debating on the formula sheet side. There will be a formula sheet. I will either provide the formula sheet to you or I'll let you make one. I haven't decided on that, so we can we're a couple weeks away from the midterm. Our first midterm will be on the fourth week. So we're a bit away from that, but there will be a formula sheet for that. And then we'll have a final exam that will be very similar to midterms 1 and 2, but the final will be cumulative, so it'll cover everything that we talked about in the class. Um, Last time I taught this class, I did homework for a grade. This year, the class is so small that the department isn't giving me a grader. So I am not going to be able to have time to grade the quizzes, the exams, and the homework on my own. So instead of making the homework be for a grade, the homework is just going to be suggested practice. So like the first problem set is there. I'll give these every week. So since we're starting on Wednesday, I think every Wednesday I'll just give you the new problem set, and then the week where we have a exam, you won't get a problem set on that week. Um, the whole point of the practice problems is so that you can practice and gain familiarity with the different kinds of questions that you might see on an exam. So part of learning is that your brain is a muscle that you have to work just like if you want to get strong at the gym, you have to lift weights. If you want to learn something complex like nuclear reactor analysis, you have to think. Part of that thinking probably involves a little bit of struggle in terms of like, I have a problem, how do I approach it? What are the right equations? What is the solving method? And that's what the suggested practice is supposed to satisfy. It allows you to get that practice outside of class to help you build up the confidence that you can do the kinds of questions that are expected of you. That way, whenever you see similar questions on the quizzes or on the exams, there won't be too many surprises, so long as you're staying on top of those practice problems. I think the number one thing I would recommend for this class is to start the practice as soon as you can. And if something has so like the practice will kind of cover about 2 lectures worth. So you might not be able to do everything on the practice after today, but you should try to do as much as you can. You basically don't want these things to build up, especially because it's a summer class and things go very quickly. Every week is equivalent to about, well, it's 10 weeks versus 16 weeks. So it's like every week is about a week and a half of a normal semester. Um, and so, yeah, the practice is really important. I would encourage you to work in groups on the practice. I encourage you to learn from each other to the extent possible. I would encourage you to use as much of your resources as you can on those things. I'll talk about AI in a bit. I would encourage you to try not to use AI, especially when you're in the learning process. Just like it's not very good practice. Like if this was like a calculus class and you had the solutions manual, it's not like the best practice to just copy everything from the solutions manual because then you're not really learning it. And that will probably be reflected in the quizzes and the exams. It's a good tool for some things, especially like if you're stuck on something and you've worked on it for a while and you're still like not making progress, that's the point where it makes more sense to like take a peek at the solution, take a peek at what ChatGPT has to say, or ask your professor or your instructor about getting questions on the things that you need help on. So if at any point you do have questions, feel free to let me know. Ideally, letting me know sooner rather than later, because again, things build up on themselves, and we don't want the work to pile up too much. And then the last part of the practice is just basically suggesting that when you're doing these problems, you put some thought into how you're organizing them so that they're readable and useful to you later. Like we'll have 3 problem sets before the first exam. You don't want to be looking at the first problem set the week before you're studying for that exam because you're going to have 2 other problem sets to do, and it's going to be a lot. Like again, things can pile up really quickly. And also when you're doing those practice problems, I would recommend almost treating it like a homework assignment in that you're organizing things, you're writing the problem statement or showing the problem statement, showing a clear workflow. That's for your benefit because if you want to review that stuff later, it's going to be a lot easier to follow a nice, well written out solution versus it's going to be to follow if you had scratch work all over the place that wasn't like well organized. So that's just my recommendation for the practice problems. And if you have questions about that, also if you have questions about anything along the way, like feel free to stop me, raise your hand or whatever. I don't mind being interrupted. Um, some of those problems might involve computers, either calculator or like Excel or like MATLAB or Python. Um, in class, the exams are going to be closed book, closed notes, no calculator. So that'll kind of help you understand or at least get appreciation for the different kinds of problems you might see. But just when you're thinking about studying for the exam, Given that you're not allowed to use a calculator, that kind of eliminates some questions that I might ask you. I wouldn't make you like write an Excel thing or like write a long computer program or do something like that on an exam if you don't have those resources in the exam, but you have all the resources available to you outside. So that's why you might end up needing some of those tools for the problem sets. Um, there's lots of resources out there. I've included most of those, or I've included a lot of that in the Google Drive, and then those extra resources could be useful. In terms of AI, this is mostly just encouraging you to try not to use it too much. Um, there is a kind of a fine line between using a tool like AI to help like accelerate your workflow and do things that you already know how to do more efficiently versus using it as like the first starting point for like building your knowledge about something. Um, I think that there's also the issue with what's mentioned in this paper by Gelrich is a phenomena called cognitive offloading, where anytime we use a new technology that helps us do things faster, we lose skills that we might have had before. Like nobody remembers phone numbers anymore because we just have the contact book in our phone. We don't memorize as many facts as we might have done before because it's very easy to Google like what's the atomic mass of a proton or what's Planck's constant. Like, I don't remember those things. I look them up if I need to. That's like examples of, I think, where the trade-off makes sense. But if you're using the technology to just like do everything for you without understanding it, it brings up issues. If you guys have ever seen the movie Wall-E, where everybody is driving around in those cars and they don't use their legs anymore because they've just got the car that'll take them everywhere. It's kind of like that. Your brain is a muscle. The way that you learn things is by using that muscle. And so that's where relying too much on those things, especially when you're still at the stage where you're trying to learn the material for the first time, is something I would try to avoid. When you get to like a job, like presumably if we're here for nuclear engineering, maybe we want to go work at a power plant or we want to go work for one of these nuclear startups. If you want to be able to bring more to the table than just like I look up the answers on ChatGPT, because anybody can look up the answers on ChatGPT. Having that's partly where like in this age of AI, having soft skills, having communication skills, and also having like detailed and domain specific knowledge about something like reactor analysis or neutronics or CFD, knowing some of that is going to be very helpful and it's going to make you a more marketable engineer whenever you're trying to like find jobs. So yeah, I would encourage you guys to be thoughtful about your use of AI. Try not to use it as a crutch. But if you're using it for things that are automating or like making your workflow faster, I think that's very useful. Throughout the course, I'll try to give us examples of areas where problems where it does great, problems where it makes mistakes, so that we also get some appreciation for the fact that like it's not a black box. Well, we look at it like a black box, um, and we might not understand exactly what's going on under the hood when it comes to like AI. And that is really important to just be aware of because it can make mistakes, it can hallucinate. And that's also part of where having domain specific knowledge is really important so that you can look at the output, but then kind of critically evaluate if the output makes sense or not. And that's only a skill that you can develop once you've gotten the specific knowledge to be able to have some kind of way to verify, like, is it telling me something that's right or is it making something up? Um, so yeah. On the sixth page, that's just kind of like a breakdown of all of the different topics that we are covering in the class. It tells you where you can find that info in the Duderstadt and Hamilton book, which is provided online, and it also lets you know like what problem sets are going to cover what chapters of the Svetcov notes. And that's the first column is the different chapters in the Svetcov notes. And then on the last page, it talks about just our assignments. Um, the quizzes aren't on there because the quizzes are kind of going to be periodic, kind of as I see fit. You might have them every class or every other class. But it does, there are firm dates for midterm exam one, midterm exam two, the final exam, and then the window over which we'll be assigned and working on the reactor design file. And I think everything else on here is more or less kind of standard university policy stuff. There's lots of various supports that are offered through the university. Oh, question? Good question. So the quizzes will always be at the beginning of class, like the first 5 or 10 minutes. So it's important to be on time. And then yeah, it'll cover stuff from the previous class. Mhm. Yeah, university policy, attendance policy, that's all standard. Makeup work, these are all university policies. The main thing with makeup work is that if you are out for any reason, if you are out and you miss a quiz or you're out and you miss an exam, you need to have a excused absence for that if you want to be able to make up what was missed. So that's mostly what the makeup policy and the absences are all about. I think the procedure is if you're out, as soon as you can, you get in contact with me to let me know, hey, I missed this day. Here's my note for the reason that I was out. And then I'll work with you in terms of scheduling the makeup. But it is on you. If you miss, it is your responsibility to do that following up and to come and make up the assignments. So yeah. I think that's the main things that I wanted to talk about on the syllabus. If you have questions about anything in the syllabus at any point, feel free to let me know. And if that's all okay, then I think I'm ready to stop talking about the syllabus and start getting into our lesson for today. So what is reactor analysis? Reactor analysis is also sometimes called reactor physics. So we are trying to understand the physics of how and why do nuclear reactors work? How do they do what they do? Um, to do that, we need to know a lot of stuff. Neutrons are like the main particle that we care about in nuclear engineering. And so we need to know when neutrons interact with stuff, what do they do? That's neutron nucleus interactions. Um, Depending on what that neutron is interacting with, those materials have different properties, like your fuel, your steel, your coolant. These different materials in your reactor have different properties that influence how your reactor works. You need to know what your neutrons are doing. You need to know how those neutrons in your reactor are distributing themselves in terms of their positions, in terms of their energies, how those things might be changing as a function of time, also how those neutrons might be distributing themselves in terms of directional angles. Um, Once we have that kind of basic background, we have the tools to start computing for a given system, how are neutrons being produced, how are neutrons being lost. If we can compute production and loss rates, then we can start setting up differential equations that say the change of my population equals all of the gain mechanisms minus all of the loss mechanisms, and then we can hopefully solve those equations or find a mathematician who can solve those equations for us so that we can start designing critical reactors. Um, Once you've got a reactor that's critical and operating at a certain power level, then you can start thinking about, I'm generating all this heat in my reactor. How do I do something useful with that? How do I set up my secondary or my tertiary power conversion loops so that I can take that energy and then convert it into steam to turn a turbine to produce electricity? Which is kind of the funny thing about nuclear anything, whether it's nuclear fission or nuclear fusion, is that we're using like some of the most complicated physics that humans have figured out to boil water. So it always comes back to boiling water at the end. But if you can do that, then you can make a power reactor. And I think nuclear power is really cool. A 1 megawatt electric nuclear power plant produces enough energy for about 400,000 homes. Nuclear power is really cool if you're thinking about the environment and climate change because it's very resource it doesn't use a lot of resources, both in terms of land, in terms of materials, and in the production of nuclear power. We're not emitting CO2. We're not emitting things into the air that are going to be contributing to climate change or emissions. So countries like France that have a lot of nuclear power have very clean air as a result of the fact that they aren't burning a bunch of stuff and throwing it into the atmosphere. So that is all very cool. That's why we like nuclear power, but we have to also be really careful when we are doing nuclear engineering because if you do things wrong, then bad things can happen. This is a picture of a reactor core. It's got fuel, it's got two loops with water flowing through them. So it's got fuel, it's got water, it's also got a graphite moderator, which aids in the thermalization of our neutrons. Um, this is a very important reactor. Does anybody know what kind of reactor this is? If you see a reactor that's got a graphite moderator and water cooling, it's probably an RBMK reactor, which is the reactor that they had at Chernobyl that went boom. So we got to know this stuff. We got to know how it works so that we know how to make it safe and so that we can yeah, so that we can do what we want to do in a way that's safe and doesn't like cause problems to the environment or people. Um, so as nuclear engineers, we have a long lineage of scientists before us who helped us get to where we are today. All these little pennies means that they got a Nobel Prize, or Mary Curie got two Nobel Prizes for the work that was done. It all kind of, if you think about nuclear stuff, it kind of starts around 1896 when Becquerel discovered radioactivity. Um, at that point, it was just they had like rocks of like uranium or some other material, and they noticed that it was giving off other particles. And as they started studying that more, they realized that those different particles could be characterized in terms of like alphas, betas, and gammas. Through learning about radioactivity, we started doing funny things like taking radioactive material and blasting that radiation onto other things to see what happened. And it's through that kind of physics and discovery that we found the electron. Around that same time, Mary and Pierre Curie they were taking uranium pitch blende and they were kind of doing elementary reprocessing of like kind of nuclear ore. That was how they discovered polonium and radium. Around a little bit later, Einstein discovered mass energy equivalence. Um, Thomson, this guy was the one that discovered the electron, and then he has descendants that ended up discovering other things. So this is Rutherford. He was Thomson's grad student, and he ended up discovering the proton. And then Chadwick, this guy, was Rutherford's PhD student, and he discovered the neutron. And so the neutron was discovered in 1932. Once you had a nuclear particle that was discovered that was neutral, that opened the door for nuclear bombs to happen. Um, it was, and people really started to put that together around 1942 when fission was discovered for the first time. Once you discovered the neutron, then you could blast things with neutrons. And when they started blasting things with neutrons, they realized, like, oh, we're producing elements that are higher up on the periodic table than we knew before because these neutrons are hitting something, they're being absorbed, and then they're transmuting into something else. So fission was discovered in 1938. 1939 is interesting because 1939 is when World War II like officially started. So the discovery of fission and the discovery of the neutron happened right before World War II. And once World War II happened, there was kind of like an arms race for building the bomb. And nuclear fission was discovered in 1938, and by 1942, we had a self-sustaining nuclear reactor under the University of Chicago called the Chicago Pile 1, where this guy, Enrico Fermi, was kind of like the lead scientist there who was they were building this reactor to demonstrate what they thought they knew about how neutrons work and how nuclear reactors work. And they ended up realizing like they had a lot of their stuff pretty well figured out at that point. Um, you go a little bit further, the X-10 reactor at Oak Ridge National Lab was one of the first power producing reactors, and they were also producing plutonium with it. And then by 1945, we did the first nuclear weapons test. So, like, very interesting period of the speed at which stuff was being discovered, and also kind of interesting. Like, that's why the Oppenheimer movie is kind of compelling and interesting because it's like at this time, with all of this science coming out, you also had World War II, and you had this kind of it's an interesting kind of combination of what was happening in the world and what was happening with physics. And so that's just kind of making us think about where we descend from as nuclear engineers. And yeah, that's just something I like to think about. Um, so kind of going along with what those early scientists were doing, they were taking like materials and they were shooting them with radiation. And so we're going to kind of imagine a similar process. We're going to imagine that we have a monoenergetic, so all of these particles have the same energy, and monodirectional, so they're all moving in the same direction, beam of neutrons that are incident on a cold, thin target that contains one nuclide. So we're going to define I is the beam intensity. So that's like what these arrows are representing, the neutrons hitting this target. Intensity is a rate per unit area at which the neutrons are striking the target. So if we think about the units, it's got units of neutrons per unit area and per unit time. So whenever I write a quantity like beam intensity I also want to make sure I'm thinking about the units of that quantity. So in this case, intensity has units of neutrons per unit area per unit time. If we define the atom density of the target with a capital N, atom density is like the number of atoms per unit volume. A density is always going to be per unit volume. So like atoms per centimeter cubed. And that would be like the atom density of this target. This target has a certain atom density. The face of this target also has a certain area A, which is this target beam interaction area. It's an area, right? So it's got area units. It's got units of centimeters squared. And then this target has a certain thickness. We'll use delta X as the little thickness of our target. And it's a thickness, so it's got units of length, and in this case, those would be centimeters. So these are the variables that we want to have in our mind when we're starting to think about these neutrons hitting this target. What would be the collision rate of all of these neutrons hitting the target? The collision rate in neutrons per second. And so the collision rate is going to depend on a couple different things. And we can kind of break this down into really two phenomena. The first one is going to be the crossing rate. Oops. Crossing rate. So that's like how many neutrons per second, how many neutrons per second are hitting this target. And it's also going to depend on the density of atoms in that area. So we can call that the areal density. And then the crossing rate and the areal density can be formulated from these different quantities that we've started with. So like if I wanted the crossing rate in neutrons per second, I could get that if I took this beam intensity and then multiplied by the area of the target. So the crossing rate would be I times A. And then the areal density, I've already got atom density, capital N. And if I took that atom density and then I multiplied by the thickness of the target, then that would give me the areal density. So the number of atoms per centimeter squared that were contained within that face of the target. So that crossing rate, it's going to depend on, or sorry, the collision rate is going to be proportional to, the little alpha means proportional to the crossing rate and to the areal density. And in this simple case, that's all that the collision rate is proportional to. And if we know that the collision rate is proportional to these two things, then we can set up an equation that relates the collision rate to what's ever on the right side. And all we would need to add is a constant of proportionality up front. And so that constant of proportionality is what we're going to call little sigma t. So that the collision rate is going to be sigma t times the crossing rate IA times the areal density n delta x. And this this sigma t, which is our proportionality constant, is a special quantity in nuclear engineering. That's called the microscopic cross section. Microscopic cross section. Cross section. And that's this guy right there. And so we want to think about what units does the microscopic cross section have? The collision rate is going to have units of neutrons per second. And if this is an equation, then the units that we have on the left side have to match the units that we have on the right side. So I'm going to kind of leave my microscopic cross section alone for a second. And I'm going to think about the other two terms that I have here. I'm just thinking about units. I times A was the crossing rate. So that had units of neutrons per second. And then the areal density had units of atoms per centimeter squared. So I know the units of every term except for my proportionality constant. And if I want to make sure I have neutrons per second on the left, then what kind of units does the microscopic cross-section have to have for my units on both sides to match up? If I want neutrons per second on the left, perfect, right? It has to be the opposite or the reciprocal of this guy. It's got to have units of centimeters squared per atom. Perfect. So we got this proportionality constant called the microscopic cross-section that has units that look like centimeters squared per atom or like area per individual atom that my neutron beam was interacting with. And that is exactly what we want to think about when we think about the microscopic total cross-section. It's a constant of proportionality that has units of area per nucleus. So you can think of the microscopic cross-section as the area of an individual nucleus. I think for a kind of high level thing in my brain that I think about for microscopic cross section, that's a perfect way to think about it. In reality, it's not exactly that because these cross sections are really like a quantum mechanical phenomena that depends on the nuclear structure of the isotope that the neutrons are hitting. And so some nuclei have very large microscopic cross sections that would be way larger than like the physical like area of an atom, but it's still very helpful to think of the microscopic cross section as the effective area that a neutron presents to a nucleus, that a neutron presents to a nucleus for a given reaction, for a given reaction. Um, so yeah, it's not 100% accurate to say that it's an area, but in terms of the calculations, in terms of a mental model to have, thinking about it like that is probably fine. Um, if you were to like look up a cross-section table and look at microscopic cross-sections, they have a funny unit. Do y'all know what the common unit for microscopic cross-section would be? It's like a farm word. Barns, right? Barns. Don't ask me where that comes from. They'll use a symbol little b for barns. And one barn, it's a very small area, the barn. It's 10 to the negative 24 centimeters squared. So these areas are teeny tiny. Um, and yeah, that's the common area unit for the microscopic cross section. And the microscopic cross section really only depends on two things. The first and probably the most obvious thing, and it depends on the type of nucleus. So like if you're talking about iron versus uranium versus carbon, those are different kinds of nuclei. Those different nuclei are going to have vastly different cross sections. And it also depends on the relative speed between the neutron and the nucleus. So that's the second thing is the relative speed between the neutron and the nucleus. Um, And yeah, that's the good that's the introductory information that we should have about the microscopic cross section. If I were to ask you, like on a quiz, if I were to give you that little symbol, little sigma t, I would ask you to be able to explain to me like what's a basic definition for it, something like this, that it's about the effective area that a neutron presents to a nucleus for a reaction. And I would probably want you to be able to tell me about the units for that thing too. You could tell me barns, you could tell me centimeters squared. It's a really good habit to get into that anytime you see a mathematical symbol in this class or in any other like physics or engineering class, terms that appear in our equations usually have units. So it's good to know like the definition. It's good to know the units if it has them, or maybe it doesn't have units. But it's good to know that either way. So that's what we would want to know about the microscopic cross section. And when we talk about the total microscopic cross section, that's related to all of the different interactions that that material could have when a neutron hits it. And so these cross sections are additive in that the total is based on mostly two different kinds of reactions. The total is mostly going to be based on absorption. So we could talk about a sigma A for absorption plus a sigma s for scattering. So that total, if a neutron hits something, it basically has two options. If there is an interaction, it's either going to be an absorption reaction or a scattering reaction. So we can combine the total as to be those two things. And absorption itself has a lot of different, there's kind of a subset of different absorption reactions that you could have. Like if a neutron hits uranium, there's a lot of different things that could happen to that neutron when it hits uranium. Can y'all think of any absorption reactions that that neutron might have when it hits like uranium, for example? Fission, right? So we could have a that would be part of absorption. We could talk about a sigma F for fission. Perfect. Thank you. E capture. Yeah. Yeah. So we can do a little sigma C for capture. Um, that's like the most common too. There's lots of funny little things that can happen when a neutron hits something. Like you can have that neutron come in, and then you can have an alpha particle come out. So you can have an N alpha reaction. You can have that neutron come in, and you can have two alphas come out. You could have a neutron come in and have three alphas come out. There's a lot of different things. So I'm just going to do a plus dot 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 for all my other absorption terms because there's a lot of them. But all of these would kind of add up. All of these different absorptions would add up to give me my sigma A. And also, my sigma S also has kind of subsets. There's different kinds of scattering reactions that we could see. Um, Two main types of scattering would be what are the two main kinds of scattering? Like even thinking back to like physics one when you had collisions. Perfect, right? Elastic and inelastic. So we could have a sigma E for elastic scattering. We could have a sigma, I'll do IN for inelastic scattering. You could have a sigma P, which is when the neutron scatters off the potential of the nucleus. You can have a sigma ER, which stands for an elastic collision with the resonance of the nucleus. And I'm just going to do a plus dot 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 because there's other scattering reactions and we probably won't interact with them very much. But it's just good to know that when we think about a sigma S and we think about a sigma A, there's lots of different things that happen within those, and those all make up the total cross section. So it's almost like if you imagine you have like a pie chart and the total pie chart is your sigma t, and then maybe it's like a nuclide where it does some absorption, and then the rest of what it does is a scatter. And then within, so this would be like all of my scattering, and these add together to give me the whole, which would be my sigma t. And within these little pieces of pie, like within my little sigma a piece of pie, I could break that out into even smaller pieces that have like my sigma f and my sigma c and all the different absorption reactions. Same thing with my sigma s. And so what that means, if we think about them as like kind of parts of if we think of these different reactions as being parts of the whole, which is the total cross section, then we can take sigma for any reaction type X and divide it by the sigma total. And that gives us the percentage or the probability that that type of reaction has in an interaction with this given material. So sigma X over sigma T, it represents the probability of a type X reaction, where that X could be any of the things we set up here. Could be fission, could be capture, could be N alpha, could be inelastic, could be elastic scattering. Um, so yeah, that is what I wanted to say about the microscopic cross section and how we can break it down into different types of reactions and also how we can think about it in terms of interaction probabilities. If we go to the next slide, that basically is just kind of listing some of the other. I think we actually covered all of the different scattering ones that I wanted to list. There's lots of other absorption reactions that you could think of. There, like we didn't mention NP, but a neutron could come in and a proton could come out. Sometimes also that sigma capture is represented with a sigma gamma. It basically means the same thing. It's like a capture, it's a radiative capture where the neutron comes in, the neutron gets absorbed into that material. That material is now excited because it absorbed the neutron, and instead of giving off a neutron or another particle like an alpha particle, it just kicks out a gamma to kind of lower its excitation energy. And also you can have like in 2N and 3N reactions where a neutron comes in and two neutrons come out, or a neutron comes in and three neutrons come out. So lots of different things that a neutron can do when it interacts with the nucleus. In general, if this interaction results in the target's nuclear structure changing, then it's an absorption reaction. Otherwise, you're just going to have things bouncing off of each other and the original nucleus's type won't change, in which case it would be a scattering reaction. So again, this list is non-exhaustive, but this is more than what you would need to know for pretty much any engineering application. Like in my research, I've never had to do anything with any of these other types except for like fission and capture. If you get into very specific niche, like nuclear materials, if you're studying cross sections themselves or trying to build out new cross section libraries, you would probably care about these more obscure ones. But for lots of purposes, we don't. So if we start talking about what these cross sections look like, we can write the cross section. The cross section is mostly can be thought of as just a function of the neutron's energy. So that's the capital E. And that cross-section influences significantly what kinds of reactions happen. And it also means that where the reaction happens, like at different neutron energies, different types of reactions become more prominent. So this is the total. In black, it's the total cross-section. In red, it's the fission cross-section. And then blue is the capture cross-section for uranium-235. And so notice that the fission cross-section graph, the red graph, is basically always on top of the blue graph, which means that for U-235, it pretty much fission is much more likely than capture. The fission cross-section is always about like an order of magnitude larger than the capture cross-section. Also notice that if you compare the fission cross-section to the total cross-section, that at least for low energies, those are like almost right on top of each other. So if it's a low energy neutron interacting with uranium-235, most of the reactions that happen are going to be fission reactions. And then once you go to higher energies, there becomes more deviation between those two. And also at low energies, this plot is like almost a perfect straight line. That means that the cross section follows a 1 over v law. So this cross section follows 1 over v, where v is the speed of the neutron at low energies. Um, so when we think about a neutron like kind of bouncing around in our reactor, like there's a fission reaction that births these neutrons. Ideally, in most of the reactors that we build, they're thermal spectrum reactors, which means that we have moderating materials like water or graphite or some other material that slows those neutrons down. Those neutrons are initially moving very fast when they come out of fission, but then they get moderated, and eventually it's almost like a little particle, like kind of bouncing around in a gas. So when those neutrons kind of become in thermal equilibrium with their surroundings, then we can talk about what their speed is. The speed corresponding to that thermal energy is about 2,200 meters per second. Its energy is about 0.025 eV. And in the first problem set, there's a good example problem to help you see where those numbers come from. Um, and so if you think about at that energy of about 0.025 eV, where we would be in terms of our cross sections, at that energy, the fission cross section is about 600 barns. And at that energy, the capture cross section is about 100 barns. So if we have a neutron in thermal equilibrium at this thermal energy, and it interacts, and that neutron interacts with uranium-235, based on these cross sections, what do we think the most likely result of that interaction is going to be? Fission, right? If the fission cross section is 600 barns and the capture cross section is 100 barns, that means the total would be 700 barns. And so the probability of fission would be 600 over 700, whereas the probability of capture would be 100 over 700. So the most likely thing that happens is that we get a fission at that energy. Um, So yeah, that's what these cross-section plots look like. We're going to talk a lot more about them as we go through, but just as like an introduction, thinking about what these cross-sections look like and how to kind of rationalize the different reaction types and what's more likely based on the probability stuff, I think that's a good example for that. When we end up doing calculations for like finding a reaction rate, we usually take the microscopic cross section and we multiply by the atom density, and that gives us the macroscopic cross section. So if I take my sigma x for some reaction and I multiply by the number density of that material, that's the definition of the macroscopic cross section. So this is definitely one of the kind of relations that we want to know, something we should probably have memorized, or at least we should memorize if we don't already have it memorized. Where N here is the atom density. Um, if I give you a material like iron, what three things do I need to compute the atom density? Sorry. Oh, just I guess just for any kind of nuclei. Like if I said, what's the atom density of iron? Um, what would you compute to get that? So you need both of those, and if you do mass over volume, you get the density, and so that's part of it. So we use rho for density. If you take density, which is in units of like kilograms per meter cubed, yeah, if you need the molar mass is going to be in the denominator, perfect. There's a capital M for the molar mass. And then the other thing you need is Avogadro's number, because that's what'll compute the number of convert back and forth between like number of particles and the amount that's there. So N sub A for Avogadro's number. So that's the molar mass. Capital M is for the molar mass. That's in units of like grams per mole. This is Avogadro's number, which is, do y'all remember Avogadro's number? 10, is it 24th or 23rd? I always forget. 23rd. Okay. And that's number of atoms or particles per mole. And then this rho, you kind of got to be careful in this class because we use rho for density, but we also use rho for something else in this class later. This in this case, this is the mass density. And so that has units of like grams per centimeter cubed or mass per unit volume. And so if you work out all of those things together, that is how you get the atom density. And as it suggests, it has units of atoms per unit volume. So like atoms per centimeter cubed would be the atom density. So if we know the units of the atom density and we know the units of the microscopic cross-section, then we can work out what kind of units the macroscopic cross-section has to have. We already said that the micro cross-section has units of atoms, sorry, has units of like centimeters squared per atom. And then we know that the number density has units of atoms per centimeter cubed. So the atoms cancel out, and 2 centimeters squared up top cancel with 2 centimeters squared on the bottom, which leaves me with just inverse centimeters, or we can say 1/centimeters. So the macroscopic cross section has units of inverse centimeters, and that is also something that has physical meaning. In terms of what a macroscopic cross section means, it's basically giving me, so it's kind of like I have a number of kinds of reactions up top. There's no units in the top, but you could think of it as just like a number of reactions. And what this is basically saying is the number of reactions that my neutron has as it travels per unit distance in the material. So that's how I think of the macro cross section is the expected number of, in this case, it would be the number of type X reactions that the neutron has per unit, do that, per unit neutron distance traveled in the material. So yeah, that's how we should be thinking about physically what is the macroscopic cross section. Expected number of reactions per neutron distance traveled through the material. And the reaction is just based on whatever, like if it was sigma F, then what that number would tell you about is the expected number of interactions that that neutron would have, the expected number of fission reactions that it would have per unit distance through that material. And the macroscopic cross section, so it depends on the number density and it depends on the micro cross section. So it's going to depend on the composition. Oops. So it's going to depend on the composition of the material. It's going to depend if we if we think about what the atom density is broken up into, it depends on the mass density. So it depends on the density of that material. Um, if you heat things up or cool things down, that also affects the density. So it also will depend on temperature. And then the micro cross section also depends on the neutron's energy. So that's the last thing, is that depends on the neutron's energy. And yeah, so that's basically everything that we want to have under our belt for what the macroscopic cross section is. It's the product of the micro cross section and the atom density, and it has units of inverse centimeters. And this is what it represents. Um, Before, when we had done our first example, it was just a simple one target material, like there was just one nuclei in the target. Now we're going to assume that that target has two different materials. It has a atom Y and it has an atom Z. And so we had already said, if we go back to where we were before with our collision rate, that the collision rate was these quantities multiplied together. And the quantity is going to change based on the type of material that the neutron is interacting with. So if I think about what my collision rate with type Y nuclei would look like, I'm going to have the intensity times the area times the thickness, and then I'm going to have the sigma total for type Y, and I'm going to have the number density for type Y materials. And like we were saying before, this product right here is the micro cross section times the number density, which is the macro cross section. That would be sigma T for atom Y. Big sigma T for atom Y. So we could also write this as I times A times delta X times sigma total for type Y nuclei. And if I wanted to write the collision rate with type Z nuclei, it would look the exact same, but I would just have total cross sections for type Z and the number density of type Z nuclei. So this would look like I A delta X times a little sigma T for type Z nuclei times the number density for the type Z nuclei. And then again, we could break that down using the definition of the macroscopic cross section to say that's the same thing as I times A times delta X times big sigma T, but for type Z nuclei. And if if the neutron beam is coming in, it can either interact with type Y or type Z. We're also thinking that this is like a thin target, which means that like there's not overlapping numbers of atoms, like there's no self-shielding from one atom at the first layer to like atoms behind it. In that case, then the two different nuclei never interfere with what another nuclei does with a neutron. If a neutron hits one nuclei, that doesn't affect what is happening with other neutrons and the other nuclei in the medium. So it's a no to do they interfere with each other. And if they don't interfere with each other, then the total collision rate in this target is going to be the collision rate for type Y nuclei plus the collision rate for type Z nuclei. We can just add them together if it's a thin target and they don't interfere with each other. So it's a sum of the Y and Z rates. And so what that means is that this is like a mixture. This could be like if I had iron and oxygen to make steel, or if I had hydrogen and oxygen to make water. If I wanted to know what's the macroscopic cross section for that mixture, this is kind of going to get me there because I can write the mixture collision rate as I times A times delta X times sigma total for the mixture. And that sigma total for the mixture is just going to be the sum of the two sigmas for the materials that made up the mixture. So I could write this as I times A times delta X times the sum of sigma T for the type Y nuclei plus the sigma T for the type Z nuclei. So in that sense, cross sections are additive. If you have a mixture, that makes it very easy to compute the cross section of a mixture. You just compute the cross sections for all the constituents, and then you add them together. So we can write down here for a mixture, sigma total for a mixture is just, I'm going to write a summation next to a sum, and we just kind of have to be careful about which is which. So from I equals 1 to n of my sigma total of type I, right? I'm I'm summing up all of my total cross sections of type I to get the mixture. And I might have n numbers of nuclei in that mixture. I just get all of their individual macro cross sections. I add them up to get the mixture cross section. And just like we were saying before, I can write this in another way by writing the definition of macro cross section, which is the micro cross section for that I nuclide times the number density for that I nuclide. And I guess I wrote this as a T, but I'm going to take that back and I'm going to make it an X because this could be any kind of reaction. This could be fission, this could be capture, this could be total, could be any type X reaction. So I think that's a better way of writing it. And this is supposed to be an equal sign, not a minus sign. So sorry if that looked bad. All right. So there is an example on the first problem set of computing cross sections for a mixture of concrete. Um, so this would be a good example of where you would need to do something like that. So yeah, that deals with cross sections both for individual nuclei and for mixtures. Once we know cross sections, we can start thinking a little bit more about the physics involved with neutrons once they interact with matter. So kind of returning to that monoenergetic, monodirectional beam hitting a target, but now instead of it being a thin target, we're going to assume that it's a thick target that goes from x equals 0 to x equals L. And we're going to define I of x to be the intensity of my uncollided beam at some distance x inside of the target. So at x equals 0, my intensity is I0. And then as my neutrons go through this material, they're going to have interactions with the different layers of the material, which is going to take away neutrons from my uncollided beam. Because every time one of the neutrons in this beam collides, it's gone from the total beam, and therefore the intensity should decrease as we go into the target. And if we wanted to understand this more, we could write just a general conservation statement for this conserved quantity, which in this case would be the intensity. So if Q is any conserved quantity, we can always write a conservation statement to try to better understand what's happening with this quantity. And that conservation statement looks like change in the quantity Q. That change is going to be due to all of the gains of that quantity Q equals the gains of Q minus all of the ways that I could be losing that quantity. So minus all the losses of Q. And this Q can really be any conserved quantity. So it can be amount of stuff. It could be a rate of, like it can be a like neutrons per second. You can think about it on that basis. You can think of it on a density basis. Anytime you have a conserved quantity, you can write a conservation statement like this. And we're going to try to do that here with the intensity of our beam. So like we're gonna imagine that we start at some location X and then we go to the location X plus a little delta X to the right. So if I imagine I'm like kind of looking at a little, if delta X is this little thickness here, then if I just look at what's between X and X plus delta X, if delta X is small, it's almost like I've got a thin target within this larger target. And I can think about my conservation of my intensity over that little interval delta X. So the change in intensity would be the intensity at X plus delta X. Change would be like in minus out or final minus initial. So it'd be my intensity at this point minus my intensity at the initial point minus the intensity at X. That's the change in intensity, right? It's just final minus initial. And that change is equal to all the ways that I could gain intensity as I go through that little delta X. If I started with this beam and it's just passing through this material, is there any way that the intensity can go up as it goes through the material? Assuming that this material doesn't like fission or produce more neutrons, then there would be no way that we could gain intensity. So the gains of intensity is going to be easy. It's just going to be a zero. And then I'm going to have minus any ways that I could lose intensity through this beam. And the way I would lose intensity is anytime my beam interacts with those materials and has a collision, then any collision is going to remove those neutrons from the beam. So my intensity loss is going to just look like my collision rate divided by the area. In this case, the intensity is neutrons per unit area per unit time. So my intensity loss is just going to look like the intensity at location X times the total cross section times the target thickness over that interval delta X. I've essentially just taken that collision rate and I've divided the area out to make the units on both sides match. So this is a equation that I could then use to get an expression for the intensity at a location X. And basically what I'm going to do is I'm going to divide both sides by delta X. So if I take this side and I divide by delta X, and I take this other side and I divide by delta X, then these delta X's are going to cancel. On the left side, I've got intensity at X plus delta X minus the intensity at X divided by the delta X. That looks very similar to almost like the way that I would approximate a derivative by doing like final minus initial over the distance. And if I were to take this whole equation and then take the limit as delta x goes to 0, then I have no delta x on the right side. So the right side isn't impacted by taking this limit. But on the left side, if I take the limit of this quantity as delta x goes to 0, that is the definition of the derivative. That's the definition of the derivative of I with respect to x. So that means that on the left side, I have di dx equals, and then on the right side, I have negative I of x times that sigma t. So this right here is the differential equation that describes how the intensity of my beam changes as it passes through the material. And to solve this differential equation, it's a first order. I guess I should go to the next slide. So we, oh, interesting. Okay, so just to recap, we found di dx is negative I of x times sigma t. And this kind of equation, if we think about the type of equation, do y'all know what kind of equation this would be? Like if I were to characterize it as a type of equation? First order, homogeneous, absolutely. So it's an ODE for sure. There's no partial derivative, so it's an ordinary differential equation. It's first order. How do we know it's first order? The highest value on my derivative, right? I don't have like second derivatives or third derivatives, so it's first order. Is it is it linear, nonlinear? And why is it linear? It that's what makes it homogeneous, is that there's no additional constant. Yeah, like perfect. Like we're trying to solve this equation for I of x. So our variable I that we're solving for, it only contains first powers. So like if I had an I squared, then it would no longer be linear. But because I just have I, it's linear. And as we said, it's homogeneous because there's no constant terms, like there's not a plus something over here. So it's homogeneous. And because of that, it's also separable. And we love separable differential equations because that means that we actually have a chance of solving it by hand. If I want to solve this equation, this differential equation, I need a piece of information to say how does my function start at the beginning. Or I basically need to know the value of my function at some point. And so in this case, I know that my intensity at x equals 0 is this initial intensity I naught. So that right there is like my initial condition. And with that initial condition, I can solve this differential equation. I can solve it by separating variables. So let's give that a try. If I have this equation, just rewrite it real quick. Then the reason that it's separable is because it only contains like multiplication and division on either side. So I can almost look at this like I want to get everything that contains one kind of variable on one side and everything that contains the other variable on the other side. So like I want to get my I of x and my di on the same side, and I want to get everything else on the other side. So like I could divide by I of x and multiply by dx, and I would get 1 over I di equals negative sigma t dx. Do y'all follow that? Just moving things around so that I have everything I like on one side and everything else, any constants or extra stuff is on the other side. And once I have my equation set up like that, I can just go ahead and integrate both sides. So I'm just going to go ahead and integrate, integrate. If I have 1 over I di, or it would be the same thing if I had the integral of 1 over x dx. What is that going to come out to? This is the one where it's not a power rule. It's ln, right? Get ln of the absolute value of x. So in that case, over here, I get the ln of the absolute value of my intensity. And then what do I get when I integrate a constant? Because that's what sigma t is here. It's just a constant. I just pick up a multiple of x, right? So I would have negative sigma t times x. And I didn't put any bounds here. So what is the other thing that I need? Plus c, perfect. I need that constant of integration. And at this point, my goal is to get an equation for I. So I'm trying to get I by itself. What do I need to do to get rid of this natural log and get I by itself? Sorry? Yeah, exponentiate both sides. So I'm going to do like e to the power of all this equals e to the power of all that. So the e and the ln cancel each other out. So I get I of x on the left-hand side. And we just got to be careful because on the right-hand side, I technically have e to the negative sigma t x plus c, where this is all inside of the exponential. Because of the rules of exponents, I can rewrite this as e to the c times e to the negative sigma tx, because e to the a plus b is the same thing as e to the a times e to the b. And then all I have left to do is to find that integration constant, which is in this case finding what e to the c is. And if I wanted to find that, I could get it by just plugging in my initial condition into this expression right here. So if I evaluate this equation at x equals 0, then I get I naught, I get e to the c, and then I have e to the negative, I'll just write it, e to the negative sigma t times 0. And e to the 0 is always going to be what? Yep, exactly. So in other words, this is just e to the c, which is my initial intensity. So I've just found that e to the c is my initial intensity. Therefore, I can substitute it back in here, and I can say that my intensity as a function of x is I naught times e to the negative sigma t x. So we took that original statement. We used conservation to set up a differential equation. We had initial condition that allowed us to solve the differential equation. And then what it tells us is that as my beam goes through this material, the neutrons get exponentially attenuated. If I started at this intensity I naught, as I increase x through the target, that intensity is like a decreasing exponential. So uncollided neutrons are exponentially attenuated as they pass through matter. And notice that this equation is very similar to what you would have seen for like radioactive decay. It's just that instead of having a sigma t here, you would have a lambda there for the decay constant, and it would be a function of time instead of a function of position. Um, that is a very good problem for me to ask you to do, like, for example, on a quiz or maybe on an exam. So if you were uncomfortable with any aspect of this problem solving process, let's talk about it. Like, let me know if you have questions, because this is something where I would expect you to be able to do something similar to this, and I would want you to show me all of the steps. I wouldn't want you to just jump to the final answer. I would want you to be able to demonstrate how you get to the final answer. So I just wanted to mention that in case at any point, if we're uncomfortable with something that we're seeing, like generally, if I'm writing it down, I'm going to expect you to be able to do that as well. So that's why it's important to follow along. If you don't have questions immediately, that's totally okay. Like I understand needing to like kind of look things over a little bit before you can formulate the questions that you want to ask. But if you're seeing something like this and you're confused, try to unconfuse yourself by thinking about it, by trying examples, and by coming and asking me or asking someone else for help if there's anything that we might be confused about. So that kind of leads us into the concept of the mean free path. Um, Oftentimes, we will want to know on average how far does a neutron go in our material before it has a collision with something. And that average path length that a neutron goes between collisions is what we call the mean free path. Mean free path. Um, And if we wanted to know the mean free path, then we need the probability that the neutron goes some distance, x, before it collides within some interval dx that's around the location x. So if we write it out in words, that's how we would write it out. And in terms of an equation, we can say that it's the collision rate in dx about x divided by the initial intensity or the initial rate that was going in. So, like as an equation, this first collision rate about in dx about x is just my intensity times my total cross section times the thickness that I'm going through dx. So we're essentially just taking the collision rate density and then or the collision rate and then multiplying by that dx. Sorry, this is the collision rate density multiplied by dx. And then we take that and we divide by the incident rate, which was just the initial intensity, which was I naught. And we just found out an analytical expression for I of x. We just found out that that I of x was I naught times e to the negative sigma tx. And then we've still got this sigma t here, and we've still got the dx there, all divided by the initial intensity I naught. And that's nice, because that means that those intensities are actually going to cancel. The I naughts are going to cancel on the top and on the bottom, which means that this probability density function, P of x dx, is going to be e to the negative sigma tx times sigma t times dx. And with that little probability function, I can then use that to go ahead and compute the average of some quantity over an interval. I basically just need the definition of the average value of a function over an interval. And that just comes from calculus. That f bar for f average is the integral from x1 to x2 of my function that I'm trying to get averaged times some weight function times dx. And then in the bottom, I have the integral from that same over that same interval of just my weight function, dx. So this is like the calculus definition of an average, where wx is a weight function. And the characteristics of that weight function, you can think of that weight function as being a probability density function. That's the way that I think about it. So characteristics of that weight function is that it is always positive. So it's always greater than or equal to 0. And it has to include a 0 on an interval. Has a 0 on the interval x going from x1 to x2. And I guess technically it could be included on the ends. So those are just like the two kind of characteristics of a probability density function. The other characteristics of a probability density function being that if you integrate that probability density function over its entire interval, what should we get? Perfect. When you integrate probability over the full interval, you get 1. So in this case, that weight function is our probability density function. So if I wanted the mean free path, then x is like the position argument that I'm averaging, and the probability density function is that quantity that we just formed right here. So I could write the mean free path like from this basic definition of an average, and then I could plug in my p of x. So just right off the bat, though, what is, if P of X is a probability density function, what we just said is that this entire denominator has to be equal to 1, right? The denominator is 1 if it's a probability integrated over its entire domain. And that means that all I really have for the mean free path is what's in the numerator. So I'm integrating from 0 to infinity of x times that p of x dx, which was sigma t times e to the negative sigma tx, and then I've got a dx. If we could integrate this, then we can get an expression for the mean free path. And we could start by just pulling the sigma t outside of the integral, right? Because it does not depend on x. So I could say this is sigma t times this integral of x times e to the negative sigma tx dx. If you were going to try to integrate this, what technique would we use? Yeah, how do you know it's integration by parts? Yeah, the way that I always think about it is basically the same. If I see two functions multiplied together, the first thing I think about is integration by parts. Because like if I think about an equation for integration by parts, I don't know if this is how y'all remember it, but I remember integral of u dv is uv minus the integral of v du. So in this case, this is what I look for when I say it's integration by parts. I look for two functions u and dv that are being multiplied together. And then if I can identify what those two things are, then I can set up what's my uv and my integral of v du. And then the only other thing that we really want to think about when with integration by parts is that when you assign u, you end up integrating it. And when you assign u, you take the derivative. And then when you assign dv, you integrate it. So when I pick these functions, I want to pick them such that u is a function that's easy to take derivatives of. Also, maybe if it's a function that I can take derivatives of and simplify the results, that's a good thing to assign for u. So like in this problem, if one of these parts of this integral is my u and the other part is my dv, which of these parts would you assign to be u? X, right? X is a really good one to pick because if my u is equal to x, then my du dx is just 1, and therefore du equals dx. And then if I've already picked my u, then my dv is everything that's left over. So in this case, my dv is going to be all of this. dv, uh, I'm going to run out of room. Sigma tx dx. And then what you do with the dv is you integrate both sides. I integrate both sides to get v. And then if I'm integrating e to the negative sigma tx, if you integrate an exponential, you get the exponential back, but then you return a constant up front, which is the reciprocal of this. So like instead of it's going to be negative 1 over sigma t times e to the negative sigma tx, right? And we know that that should be right because if I were to take the derivative of this, I should get back here. And the derivative of e to the negative sigma tx is just itself times the multiple, the derivative of the inside, which would be negative sigma t. And if I pulled that negative sigma t down, then these would all cancel each other out and I would end up right back where I started. So with that being said, that's how I could put this together. And then so if I start plugging in my integration by part stuff, I've got u times v, which is going to be x times v, which was, I'll put the negative here, 1 over sigma t e negative sigma t x. That's my uv. And then I'm doing minus the integral of v du. And my v again times e dx. That's my v times my du, which was just dx. And you got to be careful when you do integration by parts because we were originally integrating over a bound. So you want to be careful that you integrate this entire thing over those bounds. Um, and I've only got 2 minutes left. So I've set the integral up for you. It would be a good process for you to verify that what you get for this mean free path, it should come out to 1 over sigma total. So if it would be a good exercise for sometimes in books it's like exercise for the reader. A good exercise for the student would be to make sure that you could go through the steps to recover this result. But that's the definition of the mean free path. It's 1 over sigma total. So in that case, they're inversely proportional, which means that a larger mean free path is going to mean a smaller sorry, a larger total cross section is going to mean a smaller mean free path. If I have a large number of interactions per distance traveled, then the mean free path is going to be really short because I'm only going to go a little bit before I have another collision. And even though we're writing this as like a mean or as an average, there is like a probabilistic nature to these interactions. So we just want to think about and remind ourselves that these are going to be like there could be some fluctuations around that mean value. And then the only last thing I wanted to say is that this is the total mean free path, but you can write mean free paths for the other different reactions too. Like my absorption mean free path would be 1 over sigma A, and my scattering mean free path would be 1 over sigma S. Um, we are out of time, so I was going to stop there. If you guys have any questions, feel free to let me know. We can stay after. You can meet me at my office hours. You can shoot me an email. I will post these annotated slides and I'll post the video recording for today online so that you can see those if needed. And yeah, thank you guys for your time. Hope you'll have a good rest of your day, a good weekend, and I'll see you in class on Monday. Also, if you have any questions about the problem sets, any of the questions on the problem set, like over the weekend, feel free to let me know. Yeah, thank you all for your time. Have a good rest of your day. Oh, thank you, sir. And y'all take care, and I'll talk to y'all soon.
Forgot those were in the drive. So I
Oh,
usually do everything on my tablets.
yeah.
Mine's really bad on paper.
I feel yeah. I like doing my notes on the tablet too, but because it was the first day, I just wasn't sure if